What's up, crisp little baguettes? Today, we start the wonderful world of rotation. And I know what you're thinking. You're thinking, Mr. Barton, we've already done circles. You can't make me do circles again. We've talked about centripetal force and centripetal acceleration and uniform circular motion. Yes, but what about non-uniform circular motion, kids? You think everything's going to go in a perfect circle all the time for you? You're out of your mind. So, we're going to talk about rotational kinematics. And today, I'm basically just going to tell you that you already know everything about rotational kinematics. And hopefully, you believe me at the end of the video. But we'll see how you're feeling in 45 minutes. Yeah, I believe in you. Don't worry. I think you got this. I think just hold on to your chonies, and I think you'll be fine. So, without further ado, first slide. Okay, so let's first talk about why are we going to think about things rotationally, right? Mr. Barton, why do I need to learn about things going in circles? I can just make things go in straight lines. Why do I need polar coordinate systems when I can just use my beloved Cartesian coordinate systems? For those of you who are uninitiated, polar coordinate systems are. Oh, that's not the. That's not what I thought that marker was gonna look like. Um, for polar coordinate systems, there's two axes. There's the radial axis, and then there is the spherical or spherical, as some people may say. Black? Are you serious? Not that I have anything against black circles, but green. And then we have spheres that continue to radiate outwards. So the two ways that we measure for polar coordinates are let's you know what, never mind, forget that idea, delete that. Okay, the two ways that we measure spherical coordinates are how far out you go and then how far you rotate, theta. Okay. And theta is just the variable that mathematicians really love to use for angles. It's like they use n for integers, and they use what else do I don't know. Mathematicians are weird. They use weird stuff, but there's like certain variables that they use for everything. So theta is just a circle with a line through. It's a Greek letter. It means angles, right? So if you go a certain distance out and you spin, you can get to anywhere in 2D space. Cartesian, I don't know if anyone's ever told you this, but Cartesian is just an XY grid, right? You go left, right, and then up, down. So instead of going up, right, left, down, we go out and then we rotate, right? So you can still get to everywhere, right? You want to go, where do you want to go? Over there? Then you just go out, however much that is. And then you take this bad chicken right here, and then you rotate. Is that it? Almost. And then, ta-da, you got there, right? So we're spinning and going out rather than left and right and up and down. So why describe things rotationally? So let's look at this sweet rotating disc that I made for us. Okay. So we've got some points along our disc, and we want to figure out what that disc do when it spins, right? So let's put some dots real quick, just so that one will show up later. Secret dot, and then let's spin this thing. Not too far, maybe just there. Okay. So what happens when we spin it is they all travel in circular paths, right? This one's going like that. This one went like that. And then this one is following the edge of the circle. Okay. If I spin it pretty far, right? Let's spin it like 90 degrees, like that. Then we're going to go pretty far, right? We're going to do one of those, and Do one of those. Okay. So why should we describe things rotationally instead of just giving XY coordinates? Let's ask the question, how far did they go? Okay. This point right here, because it's at the center of the circle, it's at the center of rotation, this thing didn't even move. So if you're the red dot, displacement of the red dot is 0. If you're this teal dot, you went however long this thing here is, right? X teal is some distance, right? We'll call it D for distance. This pinkish dot looks like it's twice as far out, but like how much longer is this curve than this curve, right? How do I measure a curve? That distance for pink, spoiler, it's 2D, but I know a lot of geometry and you might not. So measuring this curve is kind of wonky. And then this green dot here, this green dot is even farther, maybe 3D if geometry works or something. But then we'd have to like know the radius, and you know what I mean? It's getting kind of difficult to measure these things. So if I want to know how far did these dots go, we get a bunch of weird answers for this, right? Like they're all different lengths. We have to know about how far they are from the center, the angle they rotate through, and then we have to remember how to do geometry. And let's be honest, no one knows how to do geometry. So this is a complicated thing. Let me suggest another approach. Let's just measure the angle that they travel through. So let's undo this. Let's rotate these back. Okay, so let's put maybe a line. Let's get some line tools. Let's make our line. What color do you guys want to look at? Green. Okay, so we've got a line there where they start. Okay, then we'll take this thing and we'll rotate it a little bit. We won't even rotate it 90, right? Let's put another line. There we go. Okay, here's our other line. What is the angle that they all travel through? So if we look at angles, well, this one goes whatever that angle is. And then this angle it's got the same starting side and it's got the same terminal side. So the angle that all of these go through is exactly the same. Even though they're a different distance out there, they have the same angular displacement. So if we're looking at spinning stuff, looking at the angle is a whole lot easier than looking at this curved linear distance, right? So we want to measure things angularly when things spin because it's just a little bit more natural. And then if we really want to know what is the length of this linear distance, then we've got to remember geometry. Okay. Let me tell you about one more thing in math really quick. And then we'll get on to the physics. Let me tell you about a radian. So what a radian is if I take a radius, this is all one thing. If I take this and I move this out here, and then I start there, and then I'm gonna roll it, and then as you start landing on the circle, you kind of bend it onto the circle. And let me see if I can draw that, right? It's going to look like that. You're going to bend that thing down so that we go, this distance here is equal to the radius of the circle. The angle made by this endpoint and this endpoint, the angle made by traveling one radius length around the edge of the circle is called a radian. Length equals 1 radian. And radians are another way we can measure angles instead of degrees. And as you progress in your mathematical and physics career. Um, the more you study it, the more you come to be okay with radians. You know what I mean? I feel like when you teach them to math students, they get really cranky. They're like, but Mr. Barton, degrees. What happened to degrees? Degrees were cool. I know there's 360 of them in a circle, and I know that half a circle is 180, and I know 90 is the corner of a square. Okay, but so what? Like, first of all, why do you want to cut anything into 360 pieces? Like, who looks at a pizza and thinks to themselves, you know how many pieces I should cut that thing into? 360. Nobody. They're like, how about we cut it into like 8? Because, you just half, 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 half. And this is why I don't work at Little Caesars, because my pizzas would have weird corn. Anyway, this is low key how Little Caesars cuts pizza. How annoying. But anyway, so we want to measure things angly or radially or with theta. We want to measure angles instead of linear lengths because it's easier when things go in circles. Okay. We are going to measure things in radians, and a radian is our unit of distance for rotation. Okay. Let's just familiarize you with some of the important things about radians really quick. 360 degrees is 2 pi. 180 degrees, I cut this in half, so I'll cut that in half, is just regular pi. And then 90 degrees is pi over 2. Okay, that'll get you through pretty much most of this class. And we're going to get numbers, and we're just going to slap radians on it and be like, good enough. So don't trip too much about it. The radians is not a big deal, but you're in AP physics. You should probably know what a radian is. It's a rite of passage, right? It's not something you have to learn. It's something you get to learn. All right, let's quit futzing around with this circle and go talk about how are we going to do rotational stuff. And right now I'm going to give you a huge refresher and reteach you everything we learned all semester. So the first thing we're going to do is turn all of our kinematic equations, with the exception of the one that I have a personal vendetta against, into rotational kinematic equations. The way we do that is we turn everything into its rotational equivalent. So let's talk about the rotational equivalents. Distance is no longer x. We're turning it into theta, like we talked about in the previous slide. Velocity is linear velocity. We need angular velocity. So instead of v, we use not w. This is lowercase omega. Omega. Yep. So like I am the alpha and omega. Did you guys know that Greek letters have lowercase letters? That's lowercase omega. It looks like a little W. When I write it, I'm going to do that. So this is omega. It's how fast you're spinning. Okay. Just like this is in radians. And this is in meters. This is meters per second. So this is radians per second. And the abbreviation for radians is rad. Okay. And then acceleration, meters per second squared. It turns into, this is alpha. Right? If we've got omega, we got to have alpha. And this is radians per second squared. So you kind of already notice a trend, right? Like you just turn meters into radians and now you're spinning. Okay. Let's change all these equations to your rotational kinematic equations. Final displacement is theta f equals theta initial, or not, whichever one you prefer, the 0 or the I don't care, plus omega naught t. plus 1/2 alpha t squared. And there you go. This equation accurately describes spinning stuff. It will tell you how far in an angle. So we've got a thing here. It spins to there. This equation will tell you theta, how far it's gone. If you know where it starts, how fast it's spinning, and if it's speeding up the spinning or slowing down the spinning after a certain amount of time. Same thing with velocity. You just literally change all the variables into rotating variables, and then you have the new equation. So it's omega final equals omega initial plus alpha t. That's your velocity equation for spinning stuff. Average velocity, same deal. Your average angular velocity is equal to change in angular displacement over change in time. And your average acceleration is equal to your change in angular velocity over change in time. Okay. Keep in mind these are averages. If you want to know exactly what they are, you have to use this formula or some other formula, right? These are averages. If you're speeding up the whole time, it's not going to tell you the angular velocity all the time. And the way you say these things out loud, you just throw the word angular in front of whatever you're talking about. This is angular velocity, angular acceleration, angular displacement. It's super, right? Physicists are not the most inventive people in the whole world. But maybe you're like, okay, that makes sense, right? The reason I find it just absolutely startling is because you would think if you're going to describe something moving in straight lines versus things spinning in circles, you would think it's not that easy to just change out the variables and it should work. You know what I mean? It's like you can't take your Honda Civic and if you want it to like go faster, you can't just take out the cylinders and put in bigger cylinders. Like you got to take out the motor and you got to bore out the motor and you got to change the other stuff and you got to put the blinker fluid in and you got to torque the torque things down. And you know what I mean? You can't just take this out and put that in and ta-da, it works, right? So the fact that you literally just change variables and you're like, ta-da, now it works is amazing to me. Maybe not to you, but maybe you'll learn to be amazed by it. All right. Let's talk about how do I calculate those nasty linear displacements. So if we think back to that circle thing we were talking about earlier, let me get my circle. Let me make sure it's a color we can see. Ooh, that's kind of big. Let's undo that. Let's try one more time. There we go. Okay. And then we'll put a line in there and we'll make that line heal. And okay. If we have a point on the edge of the circle and we do want to know how far linearly did it go? I rotate this thing. How far is that line? What is the length of this line here from that point to this point? If you know the radius and the angle theta, you can calculate it. The formula to go from any linear variable, if we're talking about the three like qualities of motion variables, is you take the angular one, multiply it to the radius of your circle that you're moving in, and then ta-da, you're in the linear version. Okay. So let's just make sure that we get what we think it does, right? If I go in a full circle, I go all the way around and come back to where I started, then that should give us the circumference. Ooh, my circles are bad. Of the thing, right? So I told you guys that theta, the full circle, theta is 2 pi. circumference is 2 pi r. This is the equation you learned in like 4th grade in your math class, right? And you're like, why do I care? What's pi? I want pi. Did you bring us snacks? This is the equation that you learned in 4th grade. If I substitute 2 pi into theta, I get 2 pi r. All right, let's make the leap, shall we? What's the length of any arc on a circle? This is something I didn't have memorized until I did this in college, right? What is this length L? L is the angle you go through times the radius. Of course, theta has to be in radians. This doesn't work if it's in degrees. But I feel like someone should have told me that earlier, right? Like L is just the angle times the radius, because we know this special case. It's weird that we know the special case, but not the general case. I don't know. Maybe you guys are smarter than me and you don't have any of the shortcomings I did growing up, but why don't we teach kids that like L equals theta r? Right? Anyway, maybe I'm off topic, but there you go. The arc length is theta times r. And then for the full circle, you know the special case. It's 2 pi r. Okay, cool. If you happen to want to go the other direction, then like let's say they say you want to go 3 meters around the circle. What angle does 3 meters make if your radius is 2 meters or something like that, right? Then we just solve this rearranging, for our angular variable. So you just divide all these by r. So theta is the linear distance divided by r. Omega is the linear velocity divided by r. And then alpha is the linear acceleration divided by r. Let's take a peek at units really quick to show you something else that's always irked me, and then you can just also be irked by it for the rest of your life. What are the units of displacement? Meters, Mr. Barton. Good job, kids. What's the units for the length of the radius? Meters? Yep, still meters. What's a meter divided by a meter? They cancel out, and it's unitless. Okay. But I just told you like one slide ago, one slide ago, that we measure it in radians. Why don't I get radians? For some reason in math, a radian is not a unit. Like they say radians are unitless, which I always found kind of perplexing. But I don't know. Anyway, more stuff that irritates me. So anyway, there you go. Here are your equations. Here's how you switch between angular displacements and regular displacements and back again. All right, next slide. So we've got the 3 important things that we've started the class with and we learned everything about. Displacement, velocity, acceleration. The 4th building block that we need for every other thing in physics is mass. So just like we have a spinny displacement now, theta in radians, we need a spinny mass. And an intelligent question might be, Mr. Barton, why isn't mass spinny mass? I can't just spin the mass and call it good? Not really, you can't. So there is this idea of how difficult it is to make something spin, right? Mass is how difficult it is to make something accelerate. Spinny mass is how difficult it is to make something accelerate in a circle. So that means spin faster or spin slower. It has a fancy, pretentious name. It is called the moment of inertia. Again, this is also a confusing name that mathematicians have invented for some reason. Moment does not mean like a moment of time. It means I should probably know what it means, and I feel like I don't have a great understanding. It's I don't know, it's a math thing. It's not a time thing, it's a math thing, right? There are other moments of other things, and none of them have anything to do with time. They're usually like a vector of some sort that tells you some physical quantity of something. They're called moments. You'll learn about them in calculus someday, hopefully. That's someone else's job to explain to you why it's called a moment. But the moment of inertia is spinny mass. Here's the formula for it. I is the moment of inertia, I for inertia, equals the mass of the object times the distance from the axis of rotation squared. Let me draw you a picture. Let's say you've got a thing going in a circle, and this is kind of, it's not like a circle. It's been tilted. Like this side went down, this side came up a little, and now you're looking at it's a little tilted. It's elliptical because it's in perspective. But anyway, and then we have a axis. This is where the axis intersects this plane. It's right in the center, and this thing is going to circle around this point. Basically, this is the center of the circle, and it spins around this invisible line. Okay. This distance from the center of the circle to your thing is that r. That's what we're talking about. So it's from the axis of rotation to the mass. This is for point masses. And point masses are basically, the idea is this thing has to be pretty small compared to the distance from the axis. Like marbles going around a circle, probably fine, right? Things that are not fine are if you have like a whole sphere, right? Let me shade it, right? A sphere. And then the axis of rotation goes through the center of this thing. Most of the mass is really spread out in the circle that this thing is going in. It's not mostly in one spot, right? When we say point mass, we mean most of the mass is in one spot, and you kind of have to like use your heart to determine what you mean mostly, right? Is this small enough, or is that small enough, or is that too big? Is that too much not in one spot, right? So you know what I mean. It's as good as you want it to be, and you can do some hard math to figure it out. We're not going to trip about it. Yeah. If you want to know the moment of inertia for weird shapes that are not mostly in one spot, like a sphere rotating, then there are other special formulas. You can do calculus to calculate those formulas and figure it out. But for the AP test and for this class, if I want you to do some calculation with it, I'll just tell it to you. I'll be like, the moment of inertia for a sphere spinning about an axis through its center is 2/3 mr squared. And it's usually just a fraction times mr squared. And these fractions are generally less than 1. But it's different for different shapes. Like a sphere is different from a disc, and a disc spinning this way is different from a disc spinning that way, right? So it gets pretty mathy, but moment of inertia, it's how hard it is to spin stuff or make it spin faster or slower. Here's the equation for point masses. This will get us where we need to go for today. Okay. So now let's talk about some real objects we could look at, and then we'll talk about which ones have bigger or smaller moments of inertia. Mostly for this class, you need to know, is that bigger or smaller when we're talking about the moments of inertia? What the exact value is not super duper important. So we've got three different disky things here. We have a ring. So all three of these have the same mass. So if you put this on a scale, right, and then you measure this thing, it'll say whatever, right? And then we take our scale and then we measure this one, and then it'll say the same thing. And then we put this thing on the scale and measure it, and it says the same amount. So they all weigh the same amount. They feel the same strength of gravity, but they're a little bit different shape, right? They might be different material. It's not super important. All we care about is the mass. Okay. We want to know which one has the biggest moment of inertia and which one has the smallest moment of inertia. So what we want to think about for our moment of inertia is how does mass change and how does the distribution of mass change? Is it closer to the axis of rotation or farther away? Okay, so we need to define an axis of rotation because this is definitely different than something like that, where this is kind of going into the board. You feel me? So we're going to look at this one, where this is the axis. You're kind of looking down on it. It's a pole or a pin. If we tilted these like that direction, we'd be looking like this, right? So they're spinning that direction. Okay. So our axis of rotation is straight through the center, and these are all spinning like that. Okay. They don't actually have to spin to have a moment of inertia, but for the sake of defining the axis. Okay. So we want to look at our masses and our distribution of masses. How far is it from the axis of rotation? So this one, all of our mass is on the very edge. Okay. This one, we've got some mass on the edge, right? But then I've got all this mass in there, not on the edge. So some of this mass has been redistributed closer to the axis of rotation. So if we wanted to, maybe we don't want to like do calculus, but we could think about it as chopping this into like a Russian nesting doll, like stacks of stuff. We could cut off a ring, okay? And then we could measure just the ring. And then we could cut another ring off and measure that ring. These rings are all going to have a mass smaller than m because same mass total, but this one's spread inwards. So because we've got some mass and it's closer, r is smaller, this one will have a smaller moment of inertia than this one. Okay, so things closer to the middle, closer to the axis you're spinning around, easier to turn. When we say this has a smaller moment of inertia, we're saying it resists being spun less. It's easier to spin. Okay. For the same kind of logic here, this smaller disk, it doesn't quite have the full radius as these other two disks. It has the same amount of mass, so it's like we cut off all of this outer mass, kind of melted it down or chopped it down, and then we just glued it onto this. So this one might be a little bit thicker. Maybe this one, if we lay it down, looks like this. And if we lay this one down, it looks like that. So it's thicker, but it's the same total amount of stuff, right? Because this mass in this void now has been moved inwards, closer to the axis of rotation. Again, this one has a smaller moment of inertia than this middle one. So if we want to rank them, the ring has the most. This one has the middle amount, and then this one has the least. Okay? So the closer your mass is to the center, the less moment of inertia you have. The farther away from the axis of rotation, the more you have and the harder it is to spin. The heavier it feels. Okay, cool. So that's moment of inertia. It's spinny mass. Now, let's talk about graphs, and then I think I've got 2 problems that we're going to look at. So, let's talk about graphs. Remember, theta is the same thing as x. It is our displacement. Let me change this to another color so we can see a little better. Okay. Omega is our angular velocity. It's v. And then alpha is our angular acceleration. So let's look at theta. Okay. Here's a graph for theta. This is our initial displacement. Okay. And if we're looking at x versus t graph, what does the slope represent? Well, the slope is velocity. So if we're looking at a theta versus t graph, the slope is omega, our angular velocity. Exactly the same way that our linear stuff works. For omega, for our angular velocity, if we have something like this, this y-intercept is initial angular velocity. The slope of velocity is acceleration. So the slope of angular velocity is angular acceleration, alpha. And just like in linear stuff, the area underneath this graph takes you the other direction, and it tells you the angular displacement, theta. And it actually technically tells us the change. It doesn't tell us the actual value. It just tells us how much we've changed, plus or minus. Okay. The area here, just like linear stuff, doesn't equal anything. It's meaningless. Don't ever look at the area under a displacement graph. Last one, looking at our angular stuff. The y-intercept is, of course, initial, just like the rest of them. Initial alpha. Okay. The slope, I actually don't know what the variable is for this, but it's angular jerk, right? That derivative, remember, goes jerk, snap, crackle, pop, right? But I don't know what the variable is. It's angular jerk. We're never going to look at it. Don't worry about it. And then the important part that you need to know for your AP test is the area, again, takes you that way one, and it equals the change in angular velocity. So just like linear stuff, all the same rules for graphs apply. I was going to talk to you about this slide. I think we're going to kind of hold off on it. Well, actually, let's look at it, right? I just want to tell you that things still work the way you think they do. Everything else is the same, too. Our kinetic energy is 1/2 mv squared linearly. Angularly, it's 1/2 spinny mass, moment of inertia, times omega squared. Crazy, huh? Okay. Momentum, P equals mv. There is a angular momentum. It's capital L. It's still a vector. It equals spinny mass times spinny velocity. Cool. And then force equals ma. There is a spinny force. It's actually called torque. We use the Greek letter tau for it, and it is I alpha. There's another one for force here. We'll get to that when we get to the force notes, the torque notes. But this one's going to be important for not snapping bolts, if you know what I'm saying. So everything that we've learned has an angular equivalent, and they all work pretty similar to the way that you think they do. So let's look at a couple of examples really quick, and then we'll send you on your way to fight the homework. So let's just look at a qualitative example. We're going to basically base this on your intuition and your understanding of linear stuff. And then we can get the right answer, right? We might not be able to calculate the right answer yet because we haven't learned how to find specific stuff, but we can qualitatively say what will probably happen. So, which bar will spin faster when the ball bounces off or when the ball stops? So, we've got two situations here. We've got two physics spheres approaching this bar, and the bar is free to rotate like this. Okay. We want to know which one will spin faster. If the ball comes in, hits it, and then bounces off, and now it's going that way, or when the ball comes in, same speed, hits it, and then stops, and then this thing starts to spin. And then eventually it'll hit the ball and something will happen. But we're not going to worry about that part. Okay? So which one will have a faster or a larger angular velocity? Which one will spin faster or have a larger omega? Okay, so let's think about what do we know linearly and then answer this one qualitatively. So what idea in physics should we be thinking about for things running into other things and then asking how fast they go afterwards? What does that sound like? Let's see, I've got a ball. It runs into this ball. This ball goes that way. This ball does something. How do I know how fast they're going? What did we just talk about 1 unit ago? Momentum. So let's ask ourselves some questions about momentum. All right, they're both coming in with the same initial velocity, 3 speed lines of velocity. So initial velocity is a number v. Initial velocity is v. Okay, they're identical balls, so the mass is the same. And it equals m, and the mass over here equals m as well. Okay, so their initial velocities are just mv, and they are the same for both systems. Cool. This one comes in and stops. So it goes from mv to 0. So it has a change in momentum of negative mv. Cool. This one comes in, hits it, and bounces off. And now the final is some negative number. So this one changed negative mv. It lost all of its momentum, stopped, and then turned around and kept getting more negative momentum. So our change in momentum here is greater than negative mv. Or maybe I should put less than, right? The absolute value is greater than mv. The absolute value of that too. Ignore signs, right? The number's bigger. There's a bigger change in momentum. So if this one lost more momentum, where did the momentum go? Into the bar. So this bar must have more momentum than this bar. So we can say that omega 1 final will be faster than omega 2 final because of all the momentum change. Because there's a bigger change in momentum of that ball compared to this ball. We didn't even need to know anything about spinning, and we know this one will spin faster. Isn't that tight? You don't even know anything about spinning, and you know the answer. That's so cool. All right, one more qualitative problem, and then we'll get you out of here. Okay. We want to know, what will the graph of angular acceleration of the system as a function of time look like? So the idea here is this is like a pulley, and this is a rope, and the rope is like wound around this like several hundred times. So it's not going to come undone, right? And then this is a mass, and it's pulling it that way. Okay. we're going to simplify the problem. We're going to say the pulley is heavy, right? It's got some weight to it. It's not just some rinky-dink little physics pulley for an experiment. This is a woman's pulley. You know what I mean? So it's a big kid pulley, and it's got some meat to it. So it's heavy, and it takes effort to turn, but it's frictionless. It's got really nice bearings, okay? So what's going to happen as this mass, what's the opposite color of teal? Is it red, maybe? I don't know. That's got good contrast. Okay. What's going to happen? Okay, well, it's going to fall, obviously. Do you think it will speed up or slow down or what? Well, let's look at the forces on the mass, shall we? The mass has the weight of the mass down. It's got some tension back. But if it starts from rest and starts to fall, it's going to speed up. It's going to speed up in the down direction. That means weight must be unbalanced. So there's tension. There's some pull back on it because this thing's heavy. But it's not balanced. It's going to fall. So what's gonna happen? Well, this thing has an unbalanced force. The sum of forces in the y direction are tension minus weight equals ma. And then a will be some negative number because weight's bigger than tension, right? So we're going to accelerate, but because these forces are constant, the weight is not going to change. The amount of gravity pulling on this doesn't change. If I move it down a little bit, gravity pulls just as hard. Rope, ignore the weight of the rope. It's a light rope. Okay. Tension, we don't know a bunch about tension. Maybe as this thing speeds up, there is less tension. We don't know enough about physics, right? Like, have you ever measured that? Are you sure, right? But I've measured it. So it's a good thing they put me in charge, right? So, oh no. There's something wrong here. I can't write anymore. There's something very wrong here. Oh well, we'll soldier on. So when this mass falls, it's going to accelerate, and it's going to accelerate at a constant velocity. Sorry, no, it's not. Hold tight. Sorry about that. Fixed. All right. Ooh, I can write again. Tight. So when this falls, it's not going to fall at constant velocity. It will fall with a constant acceleration. Constant. This has to be constant. Okay. It's going to accelerate at a constant rate. The acceleration of this box as a function of time will look like this. Constant. So this thing is tied to the box. So however far this box falls, it's going to pull out that much rope, and this thing will spin whatever length of rope that is. And it's going to have the same change in velocity. They're connected. So if this thing accelerates with a constant acceleration, this thing's going to accelerate with a constant acceleration. And our angular acceleration will look like that. Okay. So there you go. There's a quick and dirty, right? I said 48 minutes. But there's a video on just to get your feet wet. You're going to have a bunch of graph questions on your homework. You should feel 100% prepared for them. They're pretty simple. And if you remember this, you're good to go. There's a couple other ones that are in there that are a little weird, but remember, moment of inertia is spinny mass. The closer it is to the axis of rotation, the easier it is to spin. Mass affects it a little bit, but not as much as distance. And then you're good to go. All right. So make sure. Sorry for blinding you. Make sure to like and subscribe. If you felt strongly about this, leave a comment below. Unless it's negative. If you're gonna criticize me, just keep that to yourself, Buster. Okay. If you got something nice to say though, comment below. Otherwise, I'll see you guys next time.